So welcome everyone to this set of data infosys lectures. It's a pleasure to have Jackson Fliss here. He's going to tell us about Wilson Spool's one-loop determinants and VTCom.
Yes, great. Excellent. Hello, everyone. Jackson. It's my first time at the GFR, first time in Mumbai, first time in India. It's all very exciting for me. So thank you for having me. I'm very excited to give this lecture and then also give some further lectures later on in the week. So maybe I'll start with some introduction and some motivation, which be sufficiently broad. But so there's been a lot of progress recently in the past, I don't know, decade, 2 decades, in understanding gravity, and in particular, understanding quantum gravity as a low energy effective field theory from various different techniques, particularly gravitational path integral, but also using ADS-CFT and understanding how gravity works, at least at large distances. And one particular direction that this has been going is by thinking about gravity as a low energy effective field theory with analogy to interacting quantum systems. In particular, there's been insights from quantum information theory, been insights from studying chaos in these systems and thinking about the chaotic dynamics of gravity, and then also in similar veins, thinking about the complexity of states in quantum gravity. And this has all been very, very helpful and very, very insightful. I would like to emphasize, though, that gravity is more than just some chaotic interacting system with complex states, but it's also one that is long-range ordered, which I think is something that is of course true, but also something that has yet to be fully leveraged to the degree that I think it can be. So a lot of my research in the past years has been really thinking about gravity in this way. Hopefully this will become more clear as I go along. And so what I mean by long-range ordered here, well, of course we know that there's a very large redundancy in gravity, which comes from diffeomorphism invariance. And what this diffeomorphism invariance does for us, well, it does a couple of things. One is that there's a drastic reduction in the number of degrees of freedom. So a drastic reduction in the phase space of physical states. And this is especially true in closed spaces. So maybe you have heard the recent discussions about whether or not the Hilbert space of a closed universe is one-dimensional or not, but this certainly comes from this drastic reduction of the phase space. A separate consequence of this is that physical operators need to be dressed.
Really sorry, but in your last talk, are you going to take the view that the Hilbert space of the set is one-dimensional?
I'm going to take the view that I can treat this as a Chern-Simons path integral, and that path integral seems to indicate that the Hilbert space on a two-sphere is one-dimensional. But I'll be very agnostic and try to avoid saying controversial things. I think it's probably true. I think the arguments that I've heard make me more inclined to believe it. But whether or not, let's say, do we live in an extended Hilbert space, in which case there's only one physical state defined on the whole Cauchy slice, versus is the true Hilbert space? I don't know, but I'll try to be agnostic.
Chern-Simons theory, sorry, in Chern-Simons theory, the Hilbert space on S2 will be one-dimensional.
Yes.
But if you have decorated S2,
yes,
it would have
yeah,
dimension.
yeah, exactly.
So,
yes.
Model of physical universe, we are decorating the sphere.
This is what I was trying to hint at in this provocative last comment, is that, you know, in normal tautological phases of matter, we're very much accustomed to those being low energy phases. We project out a lot of degrees of freedom from a gap, and all the physics is determined by one state on a sphere. But of course, entanglement is something that's very, very short range sensitive, and it knows about everything about that gap. And so it knows about, it's a so-called extended Hilbert space. And whether or not we live in that or not is something I'll be agnostic about.
Decorated, you mean putting Wilson lines?
Yeah, gravitons in higher dimensions.
Oh, no, but it is just.
No, I know, yeah, in Chomsam is there, but more generally, if you don't have local degrees, you can convince yourself. Okay, sorry, go ahead.
No, this is great. Yeah, this is well, getting very close to what I want to talk about anyways. Yeah, so physical operators need to be addressed, and this renders them extended.
Sorry, just 1 minute about that. So the claim will be that even though there is a large non-trivial classical phase space,
Yes.
there is only one state in Hilbert
Yes.
space, even though there is a very large claim.
Yes.
What is this large cluster?
Stuff moving around in this account.
So
In a more general theory.
Yeah. Even it's the gravity.
but in some higher dimension.
Yeah.
Oh.
For me, gravity is 4 and higher.
I think there is a reduction from the classical phase space to there the wormhole effects are involved.
The wormhole effects are important.
No, but fine. However you argue, in the end, the claim will be even though there is a very large classical phase space, there's only one state in Hilbert.
Yes.
But I mean, it would be surprising if it was just quantizing that phase space, right?
It would be surprising to me anyway.
Yeah.
If there's a large classic.
So maybe I should also be careful though. I'm really here thinking about 2 and 3 dimensions when I said this reduces it down.
Let's wait for your last one, because I don't think it's even true in JT. This
Okay,
is what
great.
all my work has been about, and I want to tell you why it's not true in JT.
Okay, great.
Okay. But we'll wait, sorry.
Also, yeah, and also I should mention that this claim about one dimensionality of closed universes will not play any role.
Sorry.
No. But I'm here for this discussion because I'm very much interested to know, do we live in a dimensional number?
Sort of like settles the question of determinism, right?
Yeah, exactly. I in my soul, I would like to know the answer to this question, but I will not be able to answer it myself. Okay. So we have physical operators that need to be addressed, and so these operators are extended, and so now they have some interesting statistics with each other. There's of course some nice work trying to argue for how does the square locality and AD CFT. But I want to draw attention to the fact that both of these type of phenomenon are actually very familiar to us in the context of topologically ordered phases, where topologically ordered phases of matter at low energies. We also have that Hilbert spaces, despite being possibly being constructed as local path integrals over locally propagating fields, Hilbert spaces are often finite dimensional. So the Jurassic reductions of degrees of freedom, and also all the gauge invariant operators are extended.
And I know you don't want to talk about that, but in Chern-Simons, for instance, you see that finite dimension from the fact that classically there's only one configuration, right?
Yes.
So there's no analog of that there's a large classical phase space and yet a very small Hilbert space, right?
That's right. In some sense, what I want to argue for topological field theories is that in essence the local path integral is the dumbest way of writing down a theory of topological degrees of freedom, right? So you have something that is essentially just a quantum mechanics of these extended operators, and you then try to write it in terms of local fields. And of course, in doing so, there's a humongous redundancy, right? And that redundancy manifests itself as a gauge redundancy. But we like path integrals. I like path integrals, so it's one way to go. Okay. So this analogy is the sharpest in low dimensions, and that's where I'll be working for the rest of this talk and for the rest of the week and maybe for the rest of my life. But in low dimensions, so in particular in 2 and 3 dimensions, we know there are no propagating gravitons. And so all degrees of freedom are long range in some sense.
Will you allow yourself to add matter fields or not?
Yes, that's exactly what today's about.
Okay.
I'm really happy you asked that, because that is exactly what it is. And in fact, all the effective field theories of these guys are TQFTs. So in 2D, we can recast JT gravity as what's called a BF theory, where the action looks schematically as trace BF. And in 3D, we can cast gravity as it's called the Chern-Simons theory. And then this is the well-known Chern-Simons action. Yes, okay.
Relative papers by Eberhard and company with same Fliss not quite true. There's
Yes.
some other thing that replaces it. Right?
Yeah, I will also come to this. Actually, so if you allow me to be very, very schematic about this point today, tomorrow I'll focus specifically on 3D, and I'll mention this at the but at least as far as talking about things about saddles and interpretively about saddles, then we can regard this as translation.
So what is Eberhard's point, that you don't have a SN2R processor to our ADS3?
But no, it's actually it's that part is fine. The claim of Eberhard and it's more than, I think it's just correct, is that the moduli spaces of these two theories are different. There's many connections in Chern-Simons theory that are flat but don't correspond to invertible metrics. So you have to be careful about what you integrate.
Of the second order and the first order.
Yes.
Oh yeah, but that's a well-known thing, right? You have non-invertible configurations in Chern-Simons. It's no thing going back to it.
But I think what they end up concluding is that this, from here, what you would get is this SL2R Kac-Moody type algebra, right?
Well, that's also a bit different.
By Virasoro.
Because actually, so that's a question about boundary conditions, right? About what kind of configuration is going to fall off at ADS. That already, even if you were talking about Chern-Simons theory, cuts out the Kac-Moody algebra down to basically Virasoro on the boundary. Now the question is, in the bulk, what do I integrate over in the path integral? And that is something different.
Already Hanno, when he tried to do the canonical quantization with the right boundary conditions, claimed that you get basically U-will theory.
Yeah.
But I don't think he was right, as we know now. Okay, anyway, so on. So that cut down, I think.
Yeah, so indeed, there's even just talking about Chern-Simons theory with the correct boundary conditions, you're going to cut the SL2R current algebras down to just Virasoro. But then the question is actually doing the full bulk path integral. What is the right moduli space standard?
So these theories then differ on spaces with higher topology.
They differ on, actually, I think even on the spaces of fixed topology, there's still a question about what component of moduli space you would.
Yeah, but fixed and complicated topology,
Yes.
not simple topology, because
Yes,
these
right.
modular spaces then become important only for more complicated topology.
That's right. Okay. Okay, good. So now getting to Shiraz's question, how does matter affect this? And this is also something that I've been about quite a bit in the past.
I just want to
6
clarify
years.
one thing in case you're going to use it. In JT gravity, in the second order formalism, the classical phase space is not one-dimensional, right? You have someone know this much better in DS, please excuse me. But I think because you have the best case is the double-sided ADS situation, I think there's better control. And there you have an L2 worth of,
Yes, that's right.
for all renormalized lengths, right? So it's
Yes.
not the case that, you're just a one-dimensional object. You have an entire function worth of phase space there.
Yeah, but that's also true in higher dimensions. Whatnot. It's because there's a boundary where you now have this reparameterization degrees. Of freedom, right?
Exactly.
But this is also true in 3 dimensions, right? You have boundary gravitons that now keep you whole years or orbits of states.
Yes, that's right. That's right. Okay, good. I was just saying it's not like the classical description of the phase space is some very trivial phase space. You know.
No.
Okay.
Okay. So now, how does coupling and matter change things? Okay, so one way we could talk about coupling and matter and the way that has been approached in the past is just talk about what's called the semi-classical Einstein equation, right? So I would take and I would take my stress tensor source and I would put an expectation value here and some states up. And this has been one way of approaching coupling in quantum matter to gravity. Now, you should regard this equation with a lot of suspicions for several reasons. The main one is that there's a mismatch between classical functions here and quantum expectation values here. And I'm myself guilty of using this equation in a decent amount, but in different contexts. But this mismatch can become important when you say for several reasons. One, for instance, this object is badly behaved in quantum field theory. It's the unbounded below. And so it must be smeared to be made sense of. But additionally, you could have your state psi be very, very quantum. It could be, for instance, a superposition of macroscopic masses. Or even worse, it could be an entangled state of 2 moons, in which case you would start to see various inconsistencies between the fact that this is classical functions here and this is quantum equation.
You'd be able to measure which way the electron went.
Exactly.
And yet have interference.
Exactly. So this, in some sense, is a useful way of talking about semi-classical gravity, but it's even more restricted than what we normally would want to work with as gravity as an effective field theory. It's even really restricting the class of quantum states of matter that you're allowed to work. So a much better approach. Yeah.
But in some cases, it's okay. For example, if you introduce n flavors, you can be in a case where the matter system is close to classical in large limits.
Yes. And again, I'm guilty of working with this equation a decent amount. And for instance, this equation is somewhat useful when you have nice lower bounds on these on this expectation value, and then you can now talk about generalizations of, say, the Hawking-Penrose singularity theorems when you have quantum matter.
But you're always regarding this equation as an approximation.
Exactly.
Yeah, not a fundamental point.
Yeah. So a much better approach that might want to try.
Question.
Yes.
How is smearing going to help if you have the signal unbounded?
Because oftentimes, so oftentimes you can find states where this is not bounded below, and this is just because it's at a point. But for instance, we know that the Hamiltonian is bounded below by 0. So somehow if I integrate this guy over a cold Cauchy slice, I recover 0, which tells me there has to be pockets where it's positive, right? Another example is the Anneck operator, where the Anneck operator, at least in Minkowski space, is known to be bounded below, it's greater than 0. And so if I have some pocket of negative null energy, then that has to be balanced out by a decent amount of positive energy somewhere else. This is a principle known as quantum interest, that if I have some negative null energy somewhere, then there has to be overcompensated for by positive energy somewhere else. And so there's a general expectation that if I have some space-time domain D and I integrate this with some, maybe I use a different, some test function of compact support, then this object could still be negative, but it's down below by some functional of that smearing function, such that as I make this domain larger, this becomes closer to zero. That's one help for how smearing helps. Now there's a whole other direction of research that I would be glad to talk about offline because it's something else I'm interested in, but will not be very pertinent for what we're talking about today. Yeah, so I was just going to say that a much better approach to this equation is to start with the effective field theory, which is gravity plus matter, which I'll write schematically as path gravimetrics and some fundamental fields. And that Einstein-Hilbert, and I have maybe some matter action. And I just integrate out the matter. And I have some effective action of gravity here. And in this effective action of gravity, I can now vary the metric and write down some equation of motions. See if there's a new semi-classical equation of motion.
You're doing this integrating out in the vacuum state of the matter?
Yeah, but I could also have operators inserted here if I do semi-classical equation of motion. And the question is this a reasonable thing to do? Is this even possible to do? And in general, this is a very hard thing to do in practice. Just because usually, as we are very well aware of in quantum field theories, when we integrate other degrees of freedom out, we usually get a whole polynomial expansion of terms in the effective action.
But actually, if it's unless the matter is parametrically heavy, you get non-local.
Exactly. Yes.
So it's even worse than anything.
So and we'll see something non-local in just a second.
Okay.
So this is hard, and we might ask: are things easier in lower dimensions because of this topological order or long range order?
I didn't understand how this was different from that equation, semi-classical answer.
Because as Sandeep just pointed out, this will be in general non-local, and also have many polynomial terms in metric. And the question is there a controlled expansion of this where even I can think about it as just the Einstein-Hilbert plus some source term here? And that is, I think, a completely separate question than just treating treating gravity as classical while keeping the quantum system charitably quantum.
I mean, if the matter is heavy, it's a good thing. You can certainly do it. You integrate out the matter. Maybe the matter is very quantum mechanical. You know, like
Yes.
QCD effects in GR. Who cares? Integrate it out. It can all be absorbed in root GR plus corrections. And then if you're in the realm where gravity is classical, you're classical. Right? You can do a star which has nuclei made out of QCD.
Right.
Quantum stuff.
That's fair. That's fair.
But suppose the matter is not very heavy. Then is the claim that there will now be propagating degrees of freedom in this new gravity effective action that mimics the phase space of the matter,
So-
that allows you to reproduce the phase space of the matter?
Well, I think what I'm going to argue, at least in low dimensions here, is that this guy should still be the diffeomorphism invariant object, right? And so in some sense, it's going to still have topological features to it. Now, the question, it's also going to be non-local. The question is it something that that's going to be amenable to us actually working with? And let me just get to the story in 2 to 3 dimensions. Yeah.
Sorry, not to preempt, but just the question was, the matter itself, at least naively, has a non-trivial phase space.
Yes, that's right.
And will you be able to see that phase space in the?
I think, yeah, good. So that depends on if I'm allowed, I can, it's a question about how many of these operators I can insert and to what degrees they remain orthogonal and mutually independent of each other. And that is a question that I think is answerable in practice in doing this out. I'm not going to do that today. I'm going to talk about just integrating out I matter U. Yeah. Okay. So
In general, you might think that that is it.
You might think, yeah. I mean, for certain quantities, sometimes it's very dangerous to integrate out using Euclidean boundary conditions and then address, let's say, questions of causality or, you have to be careful, but with what contour you're integrating out for what question and so on. So it's a tricky game. But I feel, as you say, that it should, in spirit.
It's example because within lines you see a non-trivial phase.
yes.
You see a non-trivial, and now you see a non-trivial phase space. And would you? Yes. How would you see it in practice if you wrote down just an effective action? You're saying you get an effective action with the sources.
Yeah.
Yeah.
I mean, okay, that's sort of a toy model I had.
Yeah. Sorry, I'll shut up after this. But here you get all these higher derivatives.
Yeah.
And you might think that the equations of motion that you get from this very high derivative action produces the space of the gravitons.
Right.
So in some sense, you might hope that happens. Never seen that made.
Within an aside, but just for 2 minutes, I feel that the correct thing, if you try to do what you're saying in the matter, is to first construct the 1pi effective action, which has all the connected correlators, including those of matter.
But is it
And that will care about your state, and that will care about, and then integrate the matter out. See, then the correlation functions at the intermediate state will know all about the causality properties. See, then if you just formally integrate out the matter at that stage, it will be preserved if you're careful about that last step. But it'll be very complicated, right?
Yes.
Okay. Yeah. Sorry.
Yes. All good points. And again,
all irrelevant for what.
no. I think these are all very, very relevant. And maybe we can discuss in a bit how we can start including, say, operator insertions to explore the phase space of the matter sector. But yeah, let's first think about just integrating out just the bare action of the matter fields and talk about one-loop determinants and see how we can realize that as an effective action in topological graph. So at first pass, it seems to be hopeless because matter is going to naively spoil topological order.
What does that mean? Topological.
Well, let's be good.
Topological.
Yeah, it's because matter has propagating local degrees of freedom, legitimately local degrees of freedom. So
It'll generate an F nu squared in terms of it.
yeah, local degrees of freedom. Another fact, and this is related to also Sandeep's point, is that matter couples to the inverse metric. And so it's going to generate a non-polynomial and non-local effective action. And this is going to be even worse when we try to translate this back into the connections, which are the degrees of freedom of the topological. However, as you might think that if I'm integrating out all these fields, I'm integrating out all the local degrees of freedom. And so whatever is here is going to be gauge invariant with respect to diffeomorphism. So it feels like it should still result in some topological operator, or it should have at least still be organized by this idea of topological order or long range order. And so you might cross your fingers and hope that if I don't have any matter insertion or any operator insertions there, and I just integrate this out,
That sounds, I mean, isn't it that it depends not just on topology, but on the metric also, once you have propagating matter?
Well, so yeah, it'll be a function of the metric, but the idea is I want to think about this now as an operator sitting inside the. So let me write it out here. So let me call this Zm of G. So now I have some function of the metric, and the question is, can I think of this function as a topological operator sitting inside this? Now, of course, this is already telling us that Zm of G will be non-local. But actually, I think so. The point of this talk and the point of all the talks this week and the point of sort of a whole direction of research that I'm now going down is that it's not as bad as you might think. And in fact, we have a proposal for what this should be. So we call this proposal the Wilson spool. And let me just be careful about my context here, at least in 2D and in 3D, although maybe I can say some comments about higher D at the end of the week. This is a line operator. And it's simply expressed in terms of the topological degrees of freedom of 2D and 3D gravity.
Is the matter free here or matter in an arbitrary exaction?
Let's keep the matter free for right now. I think there's a story with interactions that we are just now starting to think about, but right now let me think it's free.
So Chern-Simons matter theory is a good example
Yes.
of thing to think about, right? So
Yes.
in that case, what is the observable that is topological? Like, there's nothing topological about Chern-Simons
So, but
as far as
so here I'm really thinking about integrating out all the matter, right?
Okay.
And there is already been a story there. The story goes back to Ogori and Bafa about how to think about that effective action in SU2 Chern-Simons theory. And in fact, our story is going to be very, very similar to theirs. But
Sorry, I missed, what was it?
the claim is that this you could ask this already in Chern-Simons matter theory. It's not even talking about gravity. And there you definitely see that you get that this is not a topological theory.
Yeah. I mean,
Yeah.
I should have said you'll get F square and
Yes.
so on.
Yes. So my claim is that I can organize all that into a single topological operator, and I'm going to make that precise. This is not going to be a hand wave. This is going to be precise reformulation. And again, this also is going to be very, very similar to the work of Ogori and Bafa back in the 90s of doing this in Chern-Simons matter theories for SU2 Chern-Simons theories. But there's going to be significant differences because these are gravitational degrees.
So just to be clear, when I say Chern-Simons matter, I don't mean massive matter. I mean massless matter, which should be distinct because
no,
a lot of this is about massless matter.
No, none of this is, yeah, I'm really thinking about this as all being massive matter.
Massive matter.
Yeah, so maybe I should have been clear at the beginning, but I want this to be massive matter, so I can really think about this as something I can integrate out and focus on at lower energies.
I see. So then why can't you do like differential expansion, derivative expansion?
You can do that, but I don't want to. I want to just integrate it out and think about everything together as a single operator. Yeah. In some sense, doing what you said is more akin to doing this semi-classical Einstein equation, where I now have an organization in terms of G Newton, and I can try to think about this as a local action organized with corrections. But
sorry, but just ask a little more about that. If it's massive, then we can say integrate it out. We get this infinite number of terms, F square, F whatever. You're saying the effect of all those you can put in as a topological.
Yes.
Seems a little strange to me because those are not topological. But
Yes, but again, whatever this object is that we've integrated out, it's sitting inside a path integral that needs to be different invariant, right?
Yes.
Whatever it is, needs to organize itself into something that is going to be different invariant with respect, right?
So it will be, for your Chern-Simons example, it would be gauge invariant.
Yes.
I agree.
So
But it won't be, I mean, I call F square a non-topological term, right?
Yes.
As opposed to A wedge dA.
yes.
And so when you say it will be a topological term, what do you mean? Or maybe you'll come to it.
I will come to it, but I mean, it's going to be legitimately a topological line operator.
Even in gauge theory, the gauge theory case.
So in the gauge theory case, again, this is a story that was worked out by Rory and Baffa, and it ends up being very.
No, but your argument here, so when you were saying, you were talking about how this resulting action is going to be different variant,
Yes.
right?
It'll
So
be
in
different
gauge
invariant.
theory, the corresponding thing you would say is gauge invariant, right? How will
Yes.
you get from there to argue that it should be topological?
Yeah, good. So one way to think about this is that let's think about what this object is, right? So it's a one-loop determinant of matter. Here's one reason why you might expect it can be topological. Besides the fact that it's sitting inside a path integral whose redundancy are diffeomorphisms. But if you're just even thinking about what this object is,
So topological means two different metrics that describe the same topology but are not diffeomorphism related will evaluate to the same action. Is that what it means?
sorry, if they are related by diffeomorphism,
Not related by diffeomorphisms, but describe the same topology.
Yeah. So different curvatures. So
Yeah.
wait, sorry,
Say I have a three-dimensional, whatever dimension you're in, I've got a metric and another metric. They describe spaces of the same topology,
yes.
but they're not diffeomorphism related. Will we get the same
So-
action evaluation?
So are you thinking about having diffeomorphisms act on the boundary of ADS or what?
No, I was thinking more generally. I mean, I'm not imposing any on-shell condition.
Yes.
So I'm in three dimensions. Total number of metrics is 3 into 2. How many is that? So it's 3 into 4 by 2. So 6 minus, six metrics. I've got 3 diffeomorphisms. So I've got 3 parameter set of non-diffeomorphism related metrics. Now off-shell, I can ask if I evaluate your object on 2 different metrics that are not diffeomorphism related, but do describe the same topology.
Let me be careful and say that if they're related by diffeomorphisms, then this will be
okay.
Yes.
But then you're just saying it's diffeomorphism invariant.
Yes.
You're not saying it's topological in the sense I should ask the same.
I'm being careful here. I want to think that this. Okay, when I write this in terms of the Chern-Simons degrees of freedom, it'll be very clear that these are line operators that only know about holonomies of the connections. Now the question is, do metrics that differ by that are not related by diffeomorphism but describe the same topology have the same holonomies is something that I don't want to necessarily pin myself down much right now.
Okay.
But it will be clear that at least that when they're related by diffeomorphisms, then this will give the exact same answer. And whether or not those different metrics give different holonomies is a different question.
So when we talk about this, is it specific to gravity or should we also try to draw parallel with Chern-Simons theory in my mind?
So the thing that's special about gravity here is that the diffeomorphisms are really tied to the gauge invariance of the theory, and so that's a bit what's special here. And this is going to lead to, I think, a pretty novel expression for what this is. Again, a lot of the story has been already worked out for SU2 Chern-Simons theories coupled to massive matter, and there will be a lot of overlap with that work. But that work, this work of Gori-Baffa will need to be modified if we want to make sense of this as one determines coupled to matter.
So is the spirit of your notion of topological that every gravity theory, even in higher dimension, would be topological from your spirit? Yeah.
No, I think there's going to be significant changes to what I'm saying in higher dimensions.
Okay.
I think that in general, this part of the story, that this is going to be some line operator is going to remain true. I think, but I don't know how to think about the disconnect between diffeomorphism invariance and topological invariance and these things in higher dimensions, just because there are propagating gravitons now. And there will be non-trivial interaction. But I think morally, there's going to be a lot of overlap with what I'm saying, but I can make, let me just say, my story is precise in 2 and 3 dimensions.
Okay.
Yeah.
Is it possible we can say a couple lines about this overview conclusion? I mean, if it is far afield.
It will, I'll make a comment on it when I get to a point where it seems it'll be natural.
Sounds like
again. Okay, let me give some hand waving motivation, and with the preface that this will be made precise. But some hand waving intuition for why we would expect something like this to be true is that if I think about what this object is, I know that I can always think about one-loop determinants, at least for minimally coupled free fields, as world-line quantum mechanics. So world-line quantum mechanics tells me that if sorry, my handwriting is worse as I get older.
Mine has always been terrible.
So the idea is that if I minimally couple matter to a metric, and at least if it's free, then I can think about this one-loop determinant as the quantum mechanics of a world line. And what I'm instructed to do in this world line quantum mechanics is integrate over all positions of all embeddings of that world line, and including if there are multiple ways of that world line of wrapping around things, including all those different wrappings. And so in some sense, it's this integration over all the embeddings of the world line that sort of gives this object this diffeomorphism, maybe careful, diffeomorphism invariant type of nature, right? So in some sense, this one-loop determinant it's integrating out all the local degrees of freedom by moving the world lines over, expanding the world lines over all different places.
And you'll be, when you say you'll finally get your Wilson lines, it'll be sort of in this spirit, right?
Yes.
Yeah. So I would say here, and not to belabor, but just to say here, for just this way you've taken a massive particle, you still care about the metric. You know?
Yeah. So this is definitely a function. This is definitely a function of the metric, and I want to now insert this into the gravitational path integral and possibly integrate over that metric. So indeed, so what to now get to the object in a precise sense, or I may say in a semi-precise sense, I'll have to either go to 2 dimensions or 3 dimensions to be 100% precise. But and it's an intermediate step. What this whole research program is doing is taking this one determinant and expressing it as an integral over line operators. All in one. Okay, so there's several things that are going on in this. So let me go down step by step.
So this was the gauge study also.
Yeah. So I've written, so here this is like a function of metric, but actually in the topological degrees freedom, this will be a connection that is roughly related to either the frame, well, actually both the frame and the spin connection, and a way that can be spelled out in a standard way in 2 and 3 dimensions. So this
is some function of.
Yes, yeah. So here, this right-hand side is a function of whatever connection I feed into it, which is in the usual way related to a metric. This is a representation that has information about the matter that I'm interested in. So in particular, it will be giving me information on its mass and its spin. So we'll be allowed to talk about massive spinning fields.
So this representation is of which group?
Depends. So if I'm in ADS-JT, it'll be SL2R. If I'm ADS3, SL2R plus SL2R. If I'm in de Sitter, then it will be representations of SU2 that should be really thought of as representations of SL2C.
And these are finite dimensional
These
representations?
will be infinite dimensional representations. Okay, good. So now this here is going to be a sum over some elementary class of non-trivial cycles of the background manifold. And what this here, so this will have some specific contour in the alpha plane, will be responsible for forcing a winding. We see that alpha appears here and it appears here. And this measure here has poles when alpha is 2 pi in. And so if no other poles sit in that alpha plane, then at the bare minimum, it's going to put an n here and sum over that n. Now, this is where I can make some connection to root alpha, which is who wrote down an operator in the effective action of SU2 Chern-Simons theory of the following form. Where now they want to think about the back reaction of matter on some local insertion of I think it was an anion. That would be the most sensible thing. But anyways, they want to look at the back reaction of matter on this, and so these would be cycles that wrapped that in amounts of times, and this is a now finite dimensional of SU2. Now
It's the dimension the matter happens to be in.
yes. So now
Represent.
this is very similar to this. However, there are interesting cases where there are more poles that appear in this alpha plane than just 2 pi in. Also, we have this sum over non-trivial cycles, and also this is the characteristic representation is very, very much different. But what's interesting is that when there are extra poles that appear, this will give very, very different answers to this than just the Ogori one.
Sorry, so just
This one, zero level question, I mean, what is there a finite sum over gamma rather than an infinite integral over some infinite dimensional space?
In some sense, that's all been captured into this, right? This guy is so this can be expanded out into a sum over saddles, where each saddle is now a different class of geodesics, and then there are wiggles about those geodesics. What I'm claiming is that I've glommed all those wiggles into geodesics into this, and all I care about now is just the summing over the classes. And again, I will also make this will come up tomorrow. In the exact match between these two descriptions.
So the geodesic, I mean, if you do the entire path integral, then the action may not look like this, right? Why does it look like such a simple exponent?
It's
Or harder exponent?
it's not trivial. There's in some sense, this guy ends up being, at least in 3 dimensions, ends up being 2 loop exact. And that itself is a non-trivial thing. You just have to work out to see how it happens.
So in the matter Chern-Simons thing, you would have a sum over all topological sectors for closed loops.
Yes.
So you'd have this, which would be different from this.
Yes.
But you've done the path integral over all the paths that lie in a particular topological sector.
Yes. Yeah, that's right.
Okay. So you've now got what remains, I mean, that P whatever is hiding a sum over an infinite number of topological sectors.
Yes, yeah. In some sense, it can be regarded as if you like, as a renormalized sum. It's a resummation of all those things, and it's just the fact that this object is invariant underneath small diffeomorphisms, right? Which are gauge transformations of the Chern-Simons.
And so, but the integrand for this is some very complicated object, right? You've done all the paths that lie in that
Yes.
topological sector. You cannot actually do that, right? It's some form.
That is that.
Yeah, we can't do this.
Wait, let's stick to, if you don't mind, to Chern-Simons for a moment. Can you actually I give you a topological sector. I take 5 loops, I give you a particular knot. And now I want to do the path integral over all particle trajectories that lie inside that knot.
Yes.
Is the claim you can actually do that, sir?
Depends on if the knot's hyperbolic or not. But if it's hyperbolic, then yes.
Hyperbolic. This is my knot.
Yeah, then that one is not hyperbolic, and I don't think I can be able to do that.
So just to ask it, if you have non-trivial linking number,
The linking is not necessarily the problem, it's whether or not there's a hyperbolic metric that can be assigned. It's okay, this is a bit of a technical point. I want to say morally, yes. I know how to do it for hyperbolic links and knots.
Just to say, if you can do it for every kind of knot, then you've solved the problem of Chern-Simon's theory with matter exactly, which sounds like a huge claim, right?
Okay.
I wouldn't believe it.
No, but again, I want to be quite careful. I'm not claiming to solve Chern-Simon's matter theory. I'm claiming that for minimally coupled matter to a metric on hyperbolic manifolds with arbitrary fundamental class, as long as they're actually hyperbolic manifolds, then I can make this matching precise.
Sorry, could we just retreat to the Chern-Simon's example?
Yes.
Not SL2R Chern-Simons, no,
Yes.
SU2 Chern-Simons.
Yes.
Okay, here in this case, to solve the Schrodinger equation of 4 particles on a sphere
No,
is a very difficult problem.
I'm not gonna make a claim about that. Again, my claim is about if I have world-line quantum mechanics on a hyperbolic manifold, then I can make this matching precise for any hyperbolic manifold with a.
But what was the Oguri buffer claim? I'm sorry to constantly repeat that, but since you talked about this SU2,
Yes.
they have some formal rewriting, is what I'm hearing.
Yes, but
the integral, the sum word topology is probably not an explicit thing, right?
Here they're not considering a sum over topologies. I think
but aren't they summing over these?
I would have to revisit the paper.
But I think they have to, because you've got, let's say you would free, if you're doing just free particles, then you just do something and then you exponentiate, and that produces all the multi-loops.
Yes, that's right.
Sort of the whole point of Chern-Simons is that this and this are different. Right?
Yes, that's right.
You can't just exponentiate, so you've got to take that exponential and divide it up in all the various topological sums, right?
Yes, that's right.
Okay, so now the question is, what is the weight for each topological sector? And then that must be what you're calling here. And the question is, can you calculate that? If you can't, you're giving a name to something you can't calculate. Is it that, or is it more? Just for the Oguri buffer.
I'm not entirely sure what the what the in full context of this was.
Okay. So just to understand the general structure that one would expect in Chern-Simon matter, it is sum over, let's say, various topological sectors, in the sense knots, let's say. Jones polynomial or whatever Wilson line expectation value times the volume.
Times the volume of all particle paths in that.
The volume of that space.
Yes.
Right? And so that weight is the non-trivial weight.
Exactly. And
so why is that also not figuring in in your gravitational example? Why is it just appearing in the single line?
All those paths are gauge equivalent. All those paths are gauge equivalent, and so this here is a gauge invariant operator.
Not all paths are gauge equivalent, right? I mean, if you have a geodesic and then kind of like that, why is it gauge equivalent?
No, so they're definitely not inequivalent paths, right? Even for fixed. So this is a manifold of fixed topology.
I mean in this, take a path which has take 2 paths which has same topology in a fixed manifold.
Yes.
There are these are gauge inequivalent paths. There can be gauge inequivalent paths, right? Of the same topology.
Yes, that's
so
right.
even that sum will be over gauge inequivalent paths.
Yes, but then this will be covered in this summing over these conjugacy classes of cycles.
But that's about a topological thing, right? That's about the paths being
It's about the fundamental group of the matter.
Yeah, so that's about topology.
Yes.
Right, but what I'm talking about is consider a path and homologically identical to it, right? So that would be
if it's a homologically equivalent path, then there's diffeomorphism that bring these two together.
Why? See, one can be a geodesic, one can be very far from a geodesic.
Yes, I don't care if they're geodesics or not. I mean, there's certainly a single geodesic in each class here, but I'm allowing these guys to be non-geodesic.
But then, I mean, all I'm saying is, if you have a geodesic and a non-geodesic, they can't be in the same gauge equivalent class.
See, I think that's why it's important that you're restricting to hyperbolic manifolds.
Yes.
No. Why?
It doesn't matter. But you can have one path which is a geodesic and one which is a non-geodesic.
Just take it.
And this is not a diffeomorphism. Of course not. A geodesic is a diffeomorphism invariant concept.
It's a free fall, right? It's a free fall, and there you have to have an engine.
No, but sorry, I can take one path. It'll be geodesic with respect to a fixed metric, right? I can now map that to a completely different path. It will definitely not be a geodesic anymore, but there's a pullback metric that I can construct.
But no, but not it's not diffeomorphism equivalent. Because the extrinsic curvature changes. Geodesic will have zero extrinsic curvature.
Are you going to tell us how you're going to do this X integral?
Tomorrow. Tomorrow I'll make this, because tomorrow I'll focus on 3 dimensions. Here
I think that's part of the question, right? Like, how are you doing the X integral?
yes, but
I'm still getting something so simple.
yes, here it's so.
But A was flat.
Yes.
If you were for some reason looking at flat connections, or G's, the metrics G corresponding to flat connections, then
Yes.
I can imagine that it doesn't really matter what specific path you're looking at, you can always deform it.
Yes, that's right. So
Is that the kind of?
I mean, eventually, I want to think about this guy sitting inside this path, which is going to localize onto flat connections indeed.
Okay.
But I also want this to be true perturbatively off shell.
Exactly, so not for any G, any
Yeah, I want this to actually be a function of G here, and as a function of it.
A, right? So that's what I guess the confusing.
Yeah, that's right. That's true. So my construction of this will be for play on hyperbolic, complete hyperbolic metrics. So these will be on shell when I actually construct this in 3D. And I also construct this using the quasi-normal node approach to the strictly from the matter sector. In which case it will be important that we are in some fixed background metric. I'd say I'm a bit confused about how this is organized in 3D, given what you say. I mean, because again, I can divide this up into different classes of cycles of world lines, and I can make this matching precisely.
Absolutely, think of it in this manner that you know, trying to figure out how, say, a geodesic and a non-geodesic are equivalent on the right hand side. They're not. So the thing that's deformed is a
Then you
geodesic
have to do that.
for a diff metric,
That's very hard.
right? For a metric that's deformed by a diff. So you could sum the left hand side within its degree of
Let's say flat space.
or
Flat space.
and then you can sum the right side and let's say 4 bit as a flat space. But then you could think of like a Fourier
Trajectory in this trajectory.
which would bring the deformed parts to the previous state parts. That's something.
I'm gonna say let's table this for tomorrow, and because I again I do have a matching between these two objects.
Now, what you said previously, which was sounded quite interesting, which is that one way to organize this sum is to do a saddle point,
Yes,
right? So you take gamma, put it along the geodesic,
yes,
and then fluctuate it, right? But and then you said it's some there's some exactness, that it's two loop
it's
exact.
two loop exact.
That will potentially give you a way to calculate it, right?
Yes, no.
That's how, is that an argument that this is how you?
Yeah, we do. So when I say I'm going to make it this matching exact, I'm going to make it exact because I'm going to do this path integral.
Okay.
And it's going to be two loop exact.
See.
And essentially, the saddle point is going to be the geodesic length of that path. Then you have fluctuations about that. The one loop term is going to turn that exponential damping with just geodesic length into a character, because it's all the one loop stuff turns basically on shell action into a character, which you can think about as this, and then the two loop term does nothing but actually makes it not a function of the mass, but a function of the highest weight of. But then after that, absolute terminates.
This is all true for any metric G? Or?
It's at least true for any complete hyperbolic.
Okay. You could imagine.
And I will say that I don't know how to do this the corresponding thing for cusp hyperbolic metrics, just because the organization of the non-perturbative part of this organization of saddle is different for complete hyperbolic versus cusp. But I think morally things are still true, but I at least know how to do this for hyperbolic.
Would it be true on S2 times S1?
This man.
His two loop exactness.
S2 cross S1.
That would make a very clear statement about the thermal partition function of free scalar field theories, which one could check.
Yes.
Which I doubt would be true.
What is the statement?
That in the world line path integral.
I don't think it's true for S2 cross S1. No.
Okay.
Yeah.
In the world line path integral is two loop exact around saddle point.
Yeah, it's not true for S2 cross S1.
It would be a great check because you're supposed to get integers.
Yeah.
And if you get that out of two loop path integral, that sounds better.
I do not
Trace equals power into rest.
I do not think it's true for
Try to say, try to make hyperbolic, and with S1, can we do Riemann surface times S1? Is that the 3 hyperbolic? Maybe not. Maybe because the S1 maybe kills that. Sorry.
I have to think about it. Yeah.
What about R2 times S1?
I can think about thermal ADS.
What?
I can think about thermal ADS.
Thermal ADS. Okay, thermal ADS. I see. So
Thermal ADS does have a one loop exact.
wait, but including the S1? Yeah. And
Because that one just has a single class. This is an infinite cyclic curve.
and so, but it's one loop exact around in world line sense.
No, in the world line sense,
in the field theory sense.
yeah.
But in the world line sense is the one.
It's two loop exact in the world line sense, but it's a one loop exact answer.
And that two loop exact reproduces the integers.
Yes. No, sorry, it reproduces the character of the CFT that you expect.
So, but if you take that two loop exact answer and expand it in a power series and e minus beta, the coefficients are all integers.
Yes.
That's amazing.
But that's just the Guillaume Maloney and Yen result, right?
So you're saying it's a lack in my education. Somehow I find it amazing, but it's probably clear.
It's let's say that for thermal ADS in the cases where this overlaps with Guillaume Maloney and Yen, we hit Guillaume Maloney and Yen.
Guillaume Maloney and Yen, they computed what determinants?
Yes, they compute one loop determinants of
using world line.
Using heat kernel.
Yes. Heat kernel. Okay. So of course you can compute one loop determinants, you'll get integers. What I find amazing is that you can reproduce that from finite number of loops around GOD6 of the world line.
Yes, that comes from the two loop exactness.
Yeah, that sounds amazing.
Yeah. Okay. Cool. So that was the introduction. So today I'm going to talk about not 3 dimensions, not hyperbolic three-dimensional spaces, but I'm going to focus even lower and just focus on 2D KT gravity. And then tomorrow I'll talk about ADS3 gravity. And then the last day, which I'm not sure when that will be, but on the last day I'll really go into the minefields and talk about DS Sitter component gravity. Maybe starting in 2D, but definitely I'll talk about the 3D story as well. And there will be extra features and subtleties that come up here, which are on top of all the features and subtleties that we are arriving at here. Okay.
Great. Can I make one quick comment?
Yes.
This process of integrating on matter with a thermal circle nowadays has become very popular. It's called thermal effective field theory. Okay. And the structure of the partition function as a function of temperature is a question of great interest in general, as a function of the geometry of the manifolds.
Yes.
And so I think what you're telling us is that thermal effective field theory, I think what we call equilibrium partition functions 20 years ago, thermal effective field theory is very simple on hyperbolic spaces for minimally coupled matter.
Yes. But also, hyperbolic spaces are very special in 2 and 3 dimensions, right?
Hyperbolic spaces are special, but
they're rigid, right?
I sort of know what it looks like on a sphere, and it's not so simple in 2 dimensions. Yeah,
yes, but also spheres are not hyperbolic.
What about that? Maybe you tell us, but if there is a one-line answer to this question, what about the hyperbolic manifold makes it?
Well, there's these rigidity theorems, right? You say that for instance, volumes are topological invariants, right? So some sense, once you know that there is, once you know a hyperbolic, complete hyperbolic metric, that is just the complete hyperbolic metric. Okay, so let's recall some basics about ADS2 GT gravity.
With no such rigidity in 2D.
Sorry, was there a question?
No, I just said no such rigidity in 2D, right?
No, but in some sense, 2D is even more rigid, and or at least JT's gravity is way more, in some sense, more rigid, just because there's everything's constrained.
One of your well-line solutions will always just be all points mapping to a point, right?
Yeah, in some sense, I'm minimally subtracting those out. Those will give a
okay. That's what gives rise to most of my complications.
Okay. Yeah.
Okay.
Yeah. There's definitely these what we call the identity components of these that in some sense gives there's always a polynomial in the mass term which needs to be matched with some renormalization condition.
I see. So you're looking at somehow the non-perturbative corrections. This is the leading thing, right?
Yes, but
this thing is what dominates, and then these other guys are small corrections on top of that.
And so
what dominates? So you would have expected that if I thought of it as a determinant of
yes,
del square plus m square.
So there's
some expansion in n.
There's loops like this that are just they're all just they shrink to a point.
Let's say,
and what I want to claim is that these loops will be divergent, but they will renormalize the mass of the scalar field. And this is some polynomial expression that, I don't know, you could insert here, and when you'd have to match to a renormalization condition. So we can match this, say, to, and this will come up later, we can match this guy to, say, a minimally subtracted key kernel, and set what that is. And for 3 dimensions, that renders this just 0. And 2 dimensions, there'll be some function of the Casimir, but it's a polynomial of mass, and this guy here will be some analytic function.
And you're not, but you're saying things that wrap the time circle once are not these.
Yes,
so this is like vacuum energy. Okay,
Yeah,
I withdraw my comment. Yeah. Okay, I get it.
Okay. So going down to 2 dimensions, the Euclidean action for gauge gravity. And I'm setting the ADS radius to 1, just so I don't have to write it out a bunch of times.
Do the double-sided case here?
No, I'm going to be very, very simple here.
Euclidean, maybe you're doing Euclidean ADS.
I'm doing Euclidean.
Okay, cigar geometries or whatever.
Okay. So as maybe we all will know that if I did not have the delta on here and I wrote down just the normal Einstein-Hilbert action, that this curve is just the Euler characteristic, and so there's actually no dynamics there. And so to have something interesting to look at, we need to actually look at a Dileton theory graph. However, even within this Dileton theory gravity, dynamics are still severely restricted because we see that phi, let me not think about the boundary right now, at least in the bulk, phi is a Lagrange multiplier. Which forces that the bigger sign, right? Yeah, is constant. And so only hyperbolic manifolds contribute to this. So up to any sort of boundary degrees of freedom, at least schematically, I just erased my main result there, but okay, we'll come up again. So organizes into a topological sum with the constant value of the Dileton being await for the volumes. So the simplest on-shell solution, the one that I'm going to focus on today, set things up.
Where is this 50 being evaluated?
In my case, it'll be at the center of the disk, but it's just a constant mode of built on actually, so it doesn't matter where it's evaluated. Right.
Oh, you're saying this just that Lagrange multiplier term.
Yeah,
So
exactly.
you're calling it 50, but just
It's
some
a
constant.
constant mode of the delta values.
You can't go beyond that line.
Is that the horizon?
Yeah.
I erased the horizon, but all right. And is there a horizon on the side too? Yeah.
Yes.
Okay. Cool. All right. So allow me to work wiggles at the end, but I'm going to wiggle out the ball wiggle discussion most of this. So the metric on this is following. And the boundary of this manifold is, or the formal boundary is where I take rho to infinity. And if you look at this and you evaluate its on-shell action, well, you get just the again the constant mode of phi. Which I would say just phi at the origin of the disk, but again it's constant or 40 Newton. And if you'd like to have some sort of picture of what this is telling us, it's if I think about taking this disk and evolving it in Lorentzian signature, then this produces a two-sided black hole, and I can think about this point of the center of the disk being the point of the bifurcated horizon, and so I should think about this as an area over 14 Newton. But I'm going to work completely on this section of this, the Euclidean section. And again, as I mentioned, for now, I will also ignore effects from the finite cutoff boundary.
Yeah, I was going to say, because otherwise you'll get a dependence from the length of the boundary. Right?
Yes, that's right.
You're not going to.
I'm not going to talk about that now. In some sense, I want to talk about all physics here. Okay, so now I want to rewrite this theory as a VF theory. Which also may or may not be well known. I'll try to go slow and step by step. But I want to think about this as an SL2R VF theory.
Bulk theory without matters and SL2R VF.
Yes, that's right. So one way we might think that this would arise that the local isometries of ADS2 are SL2R, and we want to gauge these isometries. We write down effective field of this gauge theory. So I'll write down SL2R, at least as an algebra, is the span of three generators. And I'll write it as A, 0, 1, 2. And have some computation relations that I'll write this. And eta here means twice the killing forms, which I'll take in this convention to have 1, 1 negative forms. Okay. So that's just my conventions for SL2. And now the map between the metric variables and BF variables is the following. I'm going to take a connection A. And so let's see here. 0 and 1 will be, I'll label with a little a, and then 2 will be special. So it's this guy here. So EA, PA, omega P2. And B will have the dilaton sitting inside of it. And then these auxiliary variables lambda. And I take the BF action, which is the following way, where F here is BA plus A wedge A, the normal field strength.
I'm sorry, what was P and what was omega times what? PI?
Oh, P2.
P2. What is P2?
So there's three P's.
Oh, one.
0 and 1 are in some Euclidean directions, and then 2 is it's minus sign is coming form. So it's
So this A
is 0 and 1.
points out some particular direction.
Yeah, exactly. And so in some sense, I'm thinking about the 0 and 1 as being Euclidean disk directions, and then the 2 is the time-like direction, or not the time-like direction, but it's a bit special. Okay. Good.
Modularly, it's like being dimensional.
Yeah. In a way. It's one way you can write an exception. So if I now plug in, these variables here, then what I see is that I arrive at where this is the torsion one form. So in 2 dimensions, there's only one independent component to the spin connection, so I'm just writing it as omega here. And this identifies K with 1/2 GU, at least this much.
Sorry, I'm getting totally. I've lost you. How did you? What was the relationship between BF and R?
Good. So I calculate F using this, and R is related to basically the field strength of omega.
Oh, it's the field. It's F of omega.
Yeah.
It's D omega.
Yeah, D omega wedge omega. There's terms that are E wedge E, which will give the volume form here.
I see.
Then there are terms that have DE and omega wedge E, but then it turns out these only couple to these lambdas here. So these lambdas will be Lagrange multipliers setting torsion to 0. In some sense, JT gravity, even in metric formulation, is all Lagrange multiplier times constraint, phi times curvature. It's the same thing in BF, right? BF is B here is just Lagrange multiplier times constraint, and we put all the Lagrange multipliers in the B, and then all the things we want to constrain in the A.
And so we're going to identify the field strength of this omega with actual curvature.
Yes.
Omega is the spin connection.
Yes, it is. It is.
It was spin connection in 3 dimensions.
Yeah, let's get it right. It is the what is it? The curvature, the spin connection.
Yeah.
It is the spin
it is just spin
connection.
connection.
It's just the spin connection, and D of omega is the curvature.
Oh, now I understand.
But it's in 2D, you don't even have an omega.
So these are just the usual Wehrbein fields.
Yes.
Yes.
So you've just made a choice for your Wehrbeins.
Yes.
Okay, then this is the spin connection.
Yes.
And you're writing down the usual Einstein action. Where did the you're writing down Einstein times phi.
Yes.
Yeah.
That's right.
And
substance-
R can be written as D omega. So instead of writing it as
Nice.
integral.
In some sense, you can even think about omega as being some field that's sitting in A, but then once I integrate out lambda, it really sets omega to be the torsion-free spin connection of those.
So I could have started from here.
Yeah.
And tried to rewrite it in first order format.
Yes.
And I would have got here.
Yes, exactly.
Okay.
Yes, that's exactly where you could have done. Okay, good. So that's the basic map. But I think let's keep this in mind.
Nice.
Here in mind. And then also I want to keep this in mind in case. Of course, in BF theory, it's by rescaling the dilaton, I can always, so in BF theory I can always rescale B and absorb K as long as I'm not thinking about having any sort of compact groups, which since SL2R we're not. And also in GT gravity, I can always rescale the dilaton. I think it's useful, at least for what I'm going to talk about, just to keep G Newton explicit, but it's a bit different than in higher dimensions where G Newton really is a dimension full coupling that we need to keep track of. In two dimensions here, it's a little bit.
Is this the extrinsic curvature term here?
No. So this is a bulk constraint that tells me that omega really is the torsion-free spin connection.
Oh, I see.
I left off an S boundary here.
Yeah. I see.
Because we're in the first order from.
I see.
Lambda gives like Lagrange multiplier.
Yes, yeah. So in some sense, V here is all the Lagrange multiplier. These we never even think about in the second order formalism because we've already posed that the spin connection is torsion free. And in higher dimensions, in Chern-Simons gravity, that arises as an equation of motion. And in 2D, it's really constrained. And so we put that constraint in its lambdas, and this fleshes out the whole SL2R sector for B. Okay. So now I want to think about this Poincare disk, and I can now take this metric. I can construct a set of frames, and I can construct a torsion-free spin connection from it, and I can just write down what these connections are. The important one I'll write down is A, since I want to think about actually integrating V out to arrive at both the background metric, but then also torsion-free spin connection. So one basis for A is the following. And was I inconsistent? I was inconsistent. Here, let me call this direction tau. Okay. So one thing to notice about this is that at least locally, I can realize this as Peter gauge, which is consistent with it being flat. Where G rho is e to the negative rho P1, and G tau is e to the negative tau 2. So, okay, so it's at least importantly flat, which is also commensurate with it being a non-shell hyperbolic metric. However, we're being a little bit too quick, because if it were actually truly flat, then we should get 0 for the on-shell action, and we just argue that the on-shell action of the disk is non-zero. And indeed, if we take a look at this connection, we might notice that near the origin of the disk, where rho is 0, well, this guy goes to 0, but Koch goes to 1, and we have a decal, which is the one form moving around. And so actually, this one form is not behaved there. And in fact, there's a delta function source of flux for A at the origin of the disk, which means that if I calculate what F is, at least regarding it, I can regard F as a distribution. It looks like this. And so let me draw my disk here.
Sorry, was that trace B8 that was the extrinsic curvature there?
Yeah.
Okay.
I can imagine that there's just a unit source of flux sitting in the middle of the disk that F hits. And indeed, if I now use this distributional version of F, then the on-shell BF action picks up the value of B at that origin, which will be since B is flat as well, it's just its constant value, and it's just the value of the dilaton. So it's K over 2 times phi at the origin, which is what we wanted for the on-shell. Okay, so this is important, and importantly, also for what we're about to do, inserting Wilson loops, this induces a holonomy, which if we do this if we do this carefully, we can see that the loop going around the center of the disk is, and when I use the tilde here, I mean up to conjugation by a single value group element. So that's not just means hand wave, it means that there's a that it's conjugable too. Okay.
I'm a bit confused. I thought the Reggie, so F was the Reggie. F was the Riemann tensor, right? F was d omega.
F was the omega, yes.
Okay.
And it's important actually. I'm about to get to this. It's important that guy has a flux because it might look like what I've done is I've taken something that was like possibly just a bad choice of coordinates. The fact that C tau wraps around the disk and then Kosh goes to 0. Maybe that's better with my coordinate choices. I could get rid of this, but I want to argue that's not true because yes, good. R is d omega, right?
No, I mean, because on the disk, of course, you have a exactly hyperbolic metric, right?
Yes.
No delta.
That's what I was confused.
Yeah, but
Like by the time you wrote it in terms of the A's, you
yes.
somehow introduced this delta function.
Yes, but it's all in omega. So there's no such delta function for E, right? It's all in the omega.
It's not in the omega, but I mean, there is no curvature singularity in the second order framework.
Yes. So this is completely a first order.
But it's sort of nice because in the second order by hand, you wrote this term.
Yes, in this
5 times root GR, and
Yes.
here it's automatic.
No, here and indeed, even for if I now talk about cones or try to do this topological recursion, and I go on each one, then I think you're going to pick up these sort of points where they pick out the onshell action at the right value.
Sorry, was F the same as just Ritchie scale?
Well, it's a bit. There's several terms in F, right? So I mean, F has a term that is d omega because it's dA and A has omega, but it also has dE, so it has torsion terms in E as well. Both these terms come from B wedge F, right? So here I want to think about this as being a point source in the first order formalism. I have not integrated out omega.
I mean, I was just thinking like this simple-mindedly, that A has an omega P2 component, you know? And if I did dA, you would certainly have a d omega P2 component.
Yes.
And if you look at the F there he gets, it's proportional to P2.
Yes.
So it seems like you're picking out.
No, and that's exactly what I want to say.
It seems like you're picking out d omega equal to the delta of rho d tau h d.
Yes.
That means the curvature, by the time he wrote it in first order, seems to have a delta function. Although in the second order it was smooth.
Yes.
What does it mean? I mean, if the F is curvature, then how can it have delta? What does it mean that we write it in first order or second order?
So F is not R.
No.
F is not R. At some point I thought.
So what exactly is this
By the way, he
the
marked
second
it the
order
way he
formula?
has done some choice
So-
here.
In some sense, you can think about this as picking out just the zero mode of phi, and then this would be the term that you would add in the topological coupling that you would add in by hand in second order formalism, right?
Is F R? I mean, I thought
F here we can write it out. It's dA dE plus E omega EB times EA, and then it'll have a d omega times P2. So this term will be R, it'll also have this term.
That has P2 there.
oh I see.
So
Yes.
d omega.
So that's d omega.
Yeah, this is d omega here, right?
So is F d omega?
Yes. So F has d omega.
Delta rho. Delta rho is a delta function in d omega, right?
Yes. It's a
And d omega is R. isn't
Yes.
it?
Yes.
So it seems like R has a singularity, delta function singularity.
I want to argue that it does, at least until I integrate out.
But on a
omega.
disk, R does not have any singularity.
I've done the very simple thing of taking this metric,
Yeah.
constructing a frame and constructing a spin connection from it. And then I compute
No, the question is whether R has singularity on a disk or not. You cannot get two answers if you do it two ways, right?
So
Maybe I'm mistaken.
Yeah, so something has been slightly swept under the rug cleverly in constructing his A's.
yes, but I think this is important so that I can actually reproduce this this
I
term
see
here.
what you're saying.
This needs to, you know, this is now 1/3 pi. Sorry. D omega, right? And if omega were single valued, then I would just conclude this is 0. But I know this is not 0, right?
So you're saying that instead of R being uniform in minus,
Yes.
you've sort of
It's is
collected all of that curvature at one point.
yes, maybe that's the right way of thinking about this.
Is it true? You're going to get R to be 0 everywhere else?
That's not a solution to JT gravity. Sir. That's not a solution to JT gravity. JT gravity solution is R equal to -2.
F is 0. F is 0.
What is R? That is the question. So, as I thought Omkar was proposing that in this rewriting, R has been concentrated at a point.
That's what this formula
I
says.
think so.
And flat outside.
I thought you had an extra delta function, not that it's 0 everywhere.
Oh, okay.
No, I mean this. Okay, I mean this is whether or not I do this by say saying this equal to -2 and then adding counter terms to make sure that the boundary does not give me an infinite contribution. Or, yeah.
So it's a it really is very different. Your F is very
It's very different,
from
yes.
hyperbolic space.
But I do want to point out that I think it's a pretty simple map going from this metric to this.
Look, I would have been okay if something broke down at rho equal to 0, because the coordinate system breaks down at rho equal to 0 and you use some map, right? But I'm very surprised if you compute curvature at some point where rho is not equal to 0 using your map, and you get an answer very different from the second order formalism curvature. That's very strange.
Maybe is there a -2 times theta? Like, is there an extra constant?
No. This. Sorry. Let me think. Sorry. No, actually,
That sounds strange, right?
Yeah. So good.
Maybe I'm wrong.
Sorry. Maybe actually I do mean close to rho being 0 here. But. No, but I mean, sorry. This really is flat, right?
F is 0.
So this really is flat here. This is an exact statement. It is pure gauge up to the fact that this is not one of these is not a single value group.
So F is not R, it's R plus 2.
Exactly. Yeah. No, but I mean, normally when you take a spin correction, if you just take, you have F is the Riemann tensor. Right?
No, it's R plus 2. Right? There is a volume. There's a volume in the second order first order formalism. That maybe the curvatures are related to RAB plus some epsilon EA wedge B. Right?
No, this is. I mean, this is F here, right? This is and this here is R.
So I'm making the following simple statement.
Yes.
Then you take the curvature of the spin connection.
Correct. Yes.
And that up to raising and lowering indices by Feuerbach is same as Riemann tensor.
Exactly.
Yes.
But F is not that.
F is not curvature of spin connection. Yes. Okay. So what is the curvature of the spin connection? That thing should match. Should match.
Just if that expansion that
Yes.
Jackson's written down is correct.
This is so. I mean, this is F, right?
I don't think so. I think there must be a correction term in P2.
Yeah.
I think that P2 must have a T omega plus an extra term.
No. So you think it's no? You might be right. It might be. Sorry, it might be this.
Yeah, exactly.
Okay, good.
Okay, that will explain everything.
Exactly.
Okay,
Yeah,
so then what you're really getting is R plus 2.
Yeah,
This
yes.
makes sense.
Yeah. Great.
Because otherwise it was too strange for me.
Yeah.
Only at the origin where the coordinate system breaks down, you get this. Otherwise, everywhere else, okay.
And now is the statement that the delta function is just that you're using bad coordinates.
Yeah. I mean, okay. Yeah. So
It's like using polar coordinates.
But certainly there's the important takeaway from this is that there's a non-trivial homonymy for this connection, even though the disk looked like it was completely featureless.
Yeah.
And that's, I mean, that's quite important. And in fact, there's also been comments on this. This work by Ferris and Kolkmeyer talking about entanglement entropes in JT gravity, where they want to interpret such defect operators sitting at the origin of this disk in terms of the area term of generalizations. I'm not going to go into this, but there's an analog there as well. But I just want to point out that this is a real phenomenon of this connection. That it has a non-trivial holonomy on the disk. And that's going to be important for what we're going to do with it.
One way of saying this that the map between the first and second order formalism is breaking down.
Yeah, that's one way. It's one way of thinking.
You can think of the metric as a connection everywhere away.
Is this just a bad choice of coordinates?
Yeah.
No. I want to push back on this just being a bad choice of coordinates, right? Because it really is. I mean, if it were just a bad choice of coordinates, I might think that there's, say, a single valued choice of rotating my VO binds such that I could get rid of this.
Yeah.
And that would be something that should be invariant underneath this pickup of underneath, say, things like holonomies. But here A really does have an holonomy.
But maybe you have to use two patches.
Yeah.
Okay.
And then once you do that,
That's what I would have thought, that, you can't get away with a single patch or something.
Yeah, that's fair.
But what you're saying is, you can sort of get away, except at one point.
Yeah, no, it's fair. I could do patch around here, and there's in the overlap between this patch and this patch, there's a non-single value rotation. Yes, that's fine, and I'll just shrunk this patch down to 0 cents.
That's what I think.
Okay.
so it's a little like the magnetic field of a
Yes.
monopole.
That's exactly what it is. Yes. Yeah. Okay, great. And also, thank you for spotting that.
So in the second order formalism, what is this holonomy?
If you like, it's I mean, you can even in the second order formalism, you can still talk about holonomies as spin connections, and you can still calculate that this guy would have a 2 pi holonomy.
So that I should see that if I have this kind of a geodesic that is wrapping the center, it should be the same, whatever the answer is.
So in this case, it's not G. So
not geodesic, sorry.
yeah, but so good. It's interesting because you good. This holonomy is not necessarily corresponding to the G-disc length, because there is no G-disc length associated with the cycle. It's more like what you might think of as choice, something that arises in 3 dimensions, but also in here.
Isn't it true? You take your fear bind and you parallel transport it around, it's
Yes.
not going to come back to where you
Yes.
started. And
It's like a choice.
related to the curvature inside, or
Yes.
if you like, to the non-trivial.
So the curvature inside changes, right? If I take this bigger, then I take that much. And if I take it smaller, that annulus curvature I draw. So I don't know what is this invariant thing that is coming out of, which is same no matter what is the radius of that.
It must be just at the boundary. Must be just that thing at the boundary.
The boundary must be.
It's just putting all of that in this and then doing everything singular.
So that's a logistical question. Getting close to the cutoff time, so.
I haven't even talked about that.
I was going to suggest that since you have 2 more lectures, if there's a natural stopping point, maybe in 5 or 10 minutes. That's
Well, okay. I mean, one stopping point is now, where I just don't talk about matter at all, and then I introduce matter separately, starting tomorrow. Then we might have a hard time getting through ADS3, because there's a lot of details on hyperbolic manifolds that we need to cover. So it's a bit up to you guys how you want to.
We should have a 4th lecture.
Okay.
I mean, if you are up for it.
Tuesday, Thursday. You are here till Friday.
I'm here all week.
We could do that.
Okay.
Depending on how far we get.
Great.
Questions for Jackson?
Since we haven't asked him any, it's been a really quiet talk.
Okay, like everyone's hungry. Let's thank Jackson again.